Look up on a clear night far from city lights. You will see a glowing river of stars stretching across the sky. For thousands of years people called it the Milky Way, but what is it really? It is not just a band of light. It is our home galaxy. A vast island of stars, dust and mysteries, so huge that even light takes 100,000 years to cross it. This documentary is a journey that begins here on Earth and carries us across the Milky Way. We will travel to star nurseries where suns are born, witness the explosive deaths of giant stars, and come face to face with the supermassive black hole at the heart of our galaxy. We will uncover the Milky Way's past, watch its present unfold, and peer into its distant future when it collides with another giant galaxy. Along the way, we will ask big questions. Could other worlds like ours be hidden among its billions of stars? How did this galaxy come to be? And what does its story tell us about our own place in the universe? This is not just a science journey. It is a story about us. Because every atom in our bodies was forged in the heart of a star within this very galaxy. Welcome to an entire journey through the Milky Way galaxy. On any clear night away from artificial illumination, something profound occurs above our heads. That luminescent band stretching across the celestial vault has captivated human consciousness for millennia, inspiring creation myths and cosmological wonder in every civilization that has gazed upward. The ancient Greeks called it Galaxius Kyklos, the Milky Circle. The Romans named it Via Lactea, the Road of Milk. Today we know it simply as the Milky Way. This ghostly river of light represents one of the most extraordinary optical illusions in nature. What appears as a continuous stream of luminescence is actually the combined radiance of approximately 400 billion individual stars, each separated by distances so vast that light itself requires years to traverse the emptiness between them. We are observing our home galaxy edge on from within, much like an observer standing inside a vast cosmic disk, attempting to perceive its full structure. The band's characteristic milky appearance arises from a fundamental limitation of human vision. Our eyes cannot resolve individual stellar sources at such tremendous distances, causing countless points of light to blend into what astronomers term the galactic plane. This dense concentration of stars forms the primary structural component of our galaxy. A flattened disk approximately 1,000 light-years thick and 100,000 light-years in diameter. Consider the profound implications of this perspective. Every photon entering your retina from that celestial band originated within nuclear furnaces scattered across tens of thousands of light-years. Some of that light began its journey toward Earth, when our species had not yet emerged from the African savanna. Others commenced their travels during the reign of dinosaurs, carrying information about stellar processes that occurred when our planet bore no resemblance to the world we inhabit today. The mythology surrounding this celestial phenomenon reveals humanity's instinctive recognition of its cosmic significance. Norse cultures envisioned the pathway to Valhalla. Aboriginal Australians perceived the emu in the sky, using dark dust lanes as navigational markers. Hindu tradition describes the celestial Ganges, while Lakota peoples saw the trail of spirits departing earthly existence. These diverse interpretations share a common thread, the recognition that this band of light represents something transcendent, something connecting terrestrial existence to the broader cosmos. Modern astrophysics has confirmed what ancient observers intuited through mythological frameworks. The Milky Way indeed represents a pathway not to divine realms, but to understanding our cosmic origins and ultimate destination. Every element heavier than hydrogen and helium in your body was synthesized within stellar cores scattered throughout this galactic structure. The calcium in your bones, the iron in your blood, the oxygen fueling your thoughts, all originated from nuclear processes occurring within stars whose light contributes to that band overhead. Yet what we observe represents merely a fraction of our galaxy's total stellar population. Interstellar dust, composed primarily of silicate grains and organic compounds, absorbs approximately 90% of visible light traveling through the galactic plane. This cosmic fog obscures our view of the galaxy's far side entirely, limiting optical observations to roughly 5,000 light-years, a mere 5% of our galaxy's full diameter. The revelation becomes even more staggering when we consider our observational vantage point. Earth orbits approximately 26,000 light-years from the galactic center, positioned within what astronomers designate the Orion Arm, a minor spiral structure connecting two major galactic arms. Our solar system completes one orbit around the galactic center every 240 million years, a period cosmologists term a galactic year. During Earth's existence, our planet has completed approximately 20 galactic orbits. The last time our solar system occupied its current galactic position, complex multicellular life had only recently emerged in Earth's oceans. Dinosaurs would not appear for another 150 million years. Human civilization represents less than 1/10,000th of a single galactic rotation, a temporal scale that reduces all recorded history to an astronomical instant. This perspective transforms our understanding of terrestrial permanence. The constellations we consider fixed have shifted dramatically since our last galactic circuit. Stars we observe today occupy entirely different positions relative to each other than they did during previous orbital periods. The night sky that inspired ancient astronomers bears little resemblance to the stellar configuration that will greet future civilizations 200 million years hence. The implications extend beyond mere astronomical curiosity. Our location within the galaxy directly influences Earth's habitability. The Orion Arm's position provides optimal conditions for complex life, far enough from the galactic center to avoid destructive radiation and gravitational disruption, yet close enough to benefit from the heavy element enrichment produced by successive generations of stellar nucleosynthesis. Scientists have identified this region as part of the galactic habitable zone, where conditions remain stable enough for planetary systems to develop and maintain complex chemistry over billions of years. Too close to the galactic center, and intense radiation from the supermassive black hole and frequent supernovae would sterilize planetary surfaces. Too far from the center, and insufficient heavy elements would prevent terrestrial planet formation. From our cosmic suburban location, we gaze inward toward the galactic center through the constellation Sagittarius, where 26,000 light-years distant, a supermassive black hole containing 4 million solar masses orchestrates the gravitational dance of hundreds of billions of stars. That central region, obscured by dust clouds and only observable in radio and infrared wavelengths, represents the galaxy's ancient heart, a region where stellar densities reach millions of times greater than our local neighborhood. When we look outward from the galactic center, our view encompasses the galaxy's spiral arms stretching toward the cosmic periphery, where star formation continues in vast molecular clouds containing the raw materials for future stellar generations. Each direction we observe tells a different chapter in our galaxy's biography, from the ancient stellar populations near the center to the actively star-forming regions in the outer arms. Standing beneath that band of light, we occupy a unique position in space and time. We are the first generation of humans to understand what we are observing, to recognize that Milky River as our cosmic address, and to comprehend the vast scales it represents. Every previous generation of humanity gazed upward in wonder without realizing they were looking at their galactic home from within. This recognition transforms the simple act of stargazing into something far more profound. We are not merely observing distant lights, but witnessing the architectural structure that contains our entire cosmic neighborhood. That ghostly band overhead represents the visible edge of a stellar city so vast that light requires 100,000 years to cross from one side to the other, a city containing more individual stars than there are neurons in the human brain. As we prepare to explore this cosmic metropolis in detail, we carry with us the accumulated wisdom of every human generation that has looked upward and wondered. The questions they asked about our place in the cosmos, about the meaning of existence itself, about whether we are alone, remain as compelling today as when our ancestors first developed language to articulate their cosmic curiosity. The answers we seek lie not in mythology or speculation, but in the physical reality of the galaxy itself. Within its spiral arms, stellar nurseries, and ancient stellar populations, we will discover not only the mechanisms that govern cosmic evolution, but also the story of our own origins. For in understanding the Milky Way, we begin to understand ourselves. Temporary arrangements of stellar ash that have somehow developed the capacity to contemplate the very cosmic processes that created us. Above our heads, 400 billion stars await our exploration. The familiar blue marble that has been humanity's sole reference point for existence grows smaller beneath our theoretical spacecraft. What begins as a routine departure from Earth's surface transforms into something far more profound, a complete reframing of our understanding of cosmic scale and our position within it. At an altitude of 400 kilometers, the International Space Station orbits our planet, and astronauts describe a phenomenon known as the overview effect. From this vantage point, Earth appears as a fragile oasis, suspended in an ocean of absolute darkness. The thin atmosphere that protects all life becomes visible as nothing more than a gossamer film, thinner relative to Earth than the skin of an apple. Yet this perspective, revolutionary as it may seem, represents merely the first step away from our planetary cradle. As our journey continues outward, passing the Moon at roughly 384,000 kilometers from Earth, something remarkable occurs to human perception. The Moon, which dominates our night sky and influences our tides, suddenly appears as what it truly is, a small, cratered companion to a slightly larger world, both utterly dwarfed by the emptiness that surrounds them. The entire Earth-Moon system could fit comfortably within the diameter of some individual planets in our solar system, yet from our surface-bound perspective, these objects seem to encompass the entirety of existence. At 1 million kilometers from Earth, our planet becomes indistinguishable from Venus or Mars when viewed from a similar distance. The psychological impact proves profound. Every human who has ever lived, every civilization that has risen and fallen, every war fought and peace negotiated has occurred on what now appears as an insignificant point of reflected sunlight. Carl Sagan called this perspective the pale blue dot, and its implications extend far beyond mere poetry. The journey through our solar system reveals the true nature of interplanetary space. Between Earth and Mars lies a gulf of approximately 225 million kilometers at their farthest separation. To traverse this distance at highway speeds would require 3,000 years of continuous travel. The Voyager 1 spacecraft, moving at 61,000 kilometers per hour, needed over 3 decades to escape our solar system entirely. These vast distances begin to prepare our minds for the incomprehensibly larger scales that await us in the galaxy beyond. Our Sun, that brilliant beacon that provides all energy for life on Earth, maintains its gravitational influence over a sphere roughly 100,000 astronomical units in radius. 1 astronomical unit equals the average distance between Earth and the Sun, approximately 150 million kilometers. The most distant objects in our solar system, the comets of the Oort cloud, orbit at distances up to 50,000 times farther from the Sun than Earth. Yet this entire solar system, vast beyond ordinary comprehension, occupies less than 1/10,000th of the distance to the nearest star. Proxima Centauri, our closest stellar neighbour, lies 4.24 light-years away. A light-year represents the distance light travels in 1 year, roughly 9.5 trillion kilometers. The human mind struggles to process such numbers meaningfully. If our solar system were reduced to the size of a coin, Proxima Centauri would lie approximately 500 meters away. The space between stars contains almost perfect vacuum, with fewer than 1 atom per cubic centimeter. This interstellar medium, while appearing empty, contains the raw materials from which future generations of stars and planets will form. Within this context of cosmic isolation, our solar system occupies a highly specific location within the Milky Way galaxy. We orbit not in the galactic center, where stellar densities reach extreme values, nor in the sparse outer reaches where heavy elements remain scarce. Instead, our Sun follows a nearly circular path through what astronomers designate as the Orion Cygnus Arm, also known as the Local Arm or Orion Spur. This spiral arm structure represents one of the most beautiful and complex features of our galaxy. Unlike the grand design spirals visible in distant galaxies, where 2 prominent arms dominate the structure, the Milky Way exhibits a barred spiral morphology with multiple spiral arms of varying prominence. The Orion Cygnus arm constitutes a minor spiral arm positioned between 2 major structural features. The Perseus arm lies approximately 6,500 light-years outward from the galactic center, while the Sagittarius arm extends roughly 7,000 light-years inward. Doom. Our solar system's galactic coordinates place us approximately 26,000 light-years from the galactic center, though recent measurements using improved techniques suggest this distance may be closer to 28,000 light-years. This positioning places us well within what astronomers term the galactic habitable zone, a region where stellar metallicity, the abundance of elements heavier than hydrogen and helium, reaches sufficient levels to support the formation of rocky planets while avoiding the intense radiation environment closer to the galactic core. The concept of galactic metallicity carries profound implications for the existence of complex chemistry and, by extension, life itself. The first generation of stars formed from the primordial hydrogen and helium created during Big Bang nucleosynthesis. These population 3 stars, none of which survive today, produced the first heavy elements through nuclear fusion and dispersed them throughout space when they exploded as supernovae. Subsequent generations of star formation incorporated these heavy elements, creating the carbon, oxygen, silicon, and iron essential for planet formation and biological processes. Our location within the Orion Cygnus arm places us in a region where this stellar recycling process has operated for billions of years, creating an environment rich in the elements necessary for terrestrial planets. The arm itself contains numerous star-forming regions, including the Orion Nebula, visible to the naked eye as a fuzzy star in the constellation Orion. These stellar nurseries continue the process of converting interstellar gas and dust into new stars and planetary systems. The motion of our solar system through this galactic environment follows a complex trajectory that astronomers have spent decades attempting to understand. Our Sun orbits the galactic center at a velocity of approximately 230 kilometers per second, though this speed varies depending on our position within the galactic potential well. The entire orbital period, known as a galactic year or cosmic year, requires between 225 and 250 million Earth years to complete. During each galactic orbit, our solar system experiences what astronomers call galactic seasons as we move through regions of varying stellar density and encounter different spiral arm structures. These variations in galactic environment may influence long-term climate patterns on Earth through changes in cosmic ray flux, though the precise mechanisms and their significance remain subjects of active research. The vertical motion of our solar system relative to the galactic plane adds another layer of complexity to our cosmic address. We currently lie approximately 25 light-years north of the galactic midplane and oscillate through this central disk with a period of roughly 70 million years. This oscillation carries us through regions of varying interstellar density and may correlate with certain geological and biological events in Earth's history, though again, the causal relationships remain under investigation. As we contemplate our solar system's position within this vast galactic structure, the profound isolation of our cosmic neighborhood becomes apparent. The nearest star-forming region of significant size, the Orion Nebula, lies approximately 1,350 light-years away. The nearest spiral arm of comparable size to our own, the Perseus arm, would require over 6 million years to reach at the speed of light. These distances render interstellar travel, at least with currently conceivable technology, a proposition requiring timescales comparable to geological epochs. Yet within this isolation lies a profound realization about the interconnected nature of cosmic evolution. The calcium in our bones originated in the explosive death of massive stars. The iron in our blood formed in the nuclear furnaces of stellar cores. The oxygen we breathe resulted from billions of years of stellar nucleosynthesis and planetary evolution. Though separated by vast distances from the nearest stellar neighbors, our existence depends entirely on the galactic ecosystem that surrounds us. The spiral arm that serves as our cosmic neighborhood represents far more than a mere collection of nearby stars. It constitutes a dynamic, evolving structure where the ongoing processes of stellar birth, evolution, and death continue to shape the galactic environment. Understanding our position within this system provides the foundation for comprehending the larger galactic community we are about to explore, where hundreds of billions of stars participate in the grand cosmic dance that has continued for over 13 billion years. Our galaxy stretches 100,000 light-years from edge to edge. Within this colossal disk of stars, gas and dark matter, approximately 200 billion suns trace their orbital paths through space. The Milky Way stands as one of the most massive galaxies in our local cosmic neighborhood. Yet from our position embedded deep within its structure, mapping its true architecture presents an extraordinary challenge. Astronomers classify our galaxy as a barred spiral, a designation that reveals fundamental characteristics about its formation and evolution. The spiral arms that define its structure are not rigid features carved in stone, but dynamic density waves that compress interstellar material as they propagate through the galactic disk. These compression zones trigger the collapse of molecular clouds, igniting regions of intense star formation that illuminate the spiral pattern in brilliant blue light. At the galaxy's heart lies a dense central bulge, an ellipsoidal concentration of ancient stars that formed during the Milky Way's earliest epochs. This bulge extends roughly 10,000 light-years from the galactic center, populated by metal-poor stars whose spectra reveal the chemical composition of the primordial universe. These stellar fossils carry within their atmospheres the signatures of nucleosynthesis from the first generations of massive stars. The central bar structure, approximately 27,000 light-years in length, rotates as a coherent gravitational feature. This bar channels gas inward toward the galactic nucleus while simultaneously launching spiral density waves outward into the disk. The bar's gravitational influence extends far beyond its visible boundaries, affecting stellar orbits throughout the inner galaxy and maintaining the spiral pattern through complex resonance mechanisms. 4 major spiral arms emerge from the central bar region. The Perseus arm and the Sagittarius arm represent the galaxy's most prominent spiral features, while the Norma arm and the Scutum Centaurus arm complete the primary structure. These arms contain the highest concentrations of massive young stars whose intense ultraviolet radiation ionizes surrounding hydrogen clouds, creating the spectacular emission nebulae that trace the spiral pattern across electromagnetic wavelengths. Our solar system occupies a position within a minor spiral feature designated the Orion Cygnus arm, also known as the local arm. This structure represents a bridge or spur connecting the Perseus and Sagittarius arms, rather than a major spiral arm itself. Our location places us approximately 26,000 light-years from the galactic center, positioned roughly halfway between the galaxy's nucleus and its outer edge. This suburban location within the galactic disk provides optimal conditions for the development and maintenance of complex chemistry necessary for biological processes. The galactic disk itself exhibits remarkable thinness relative to its diameter. While spanning 100,000 light-years in width, the stellar disk maintains an average thickness of only 1,000 light-years. This extreme aspect ratio creates a structure resembling a cosmic coin, with most stellar material concentrated within a relatively narrow plane. The disk's vertical structure reveals itself through careful analysis of stellar kinematics, with older populations exhibiting greater scale heights due to gravitational scattering over cosmic time. Surrounding the visible disk extends an enormous spherical halo, reaching distances exceeding 200,000 light-years from the galactic center. This halo contains globular clusters, ancient stellar associations that formed during the galaxy's earliest assembly phases. The halo also harbors the mysterious dark matter component, an invisible gravitational scaffold that comprises approximately 90% of the galaxy's total mass. Dark matter's gravitational influence shapes the rotation curve of the galactic disk, maintaining orbital velocities that would otherwise be impossible given the visible matter content alone. Mapping the Milky Way's structure requires sophisticated observational techniques, as our embedded position within the galactic plane severely limits optical observations. Interstellar dust absorbs and scatters visible light, creating apparent voids in star counts that historically misled astronomers about the galaxy's true extent. The Great Rift, a prominent dark lane visible along the summer Milky Way, represents one such dust lane rather than an absence of stars. Radio astronomy revolutionized galactic cartography by penetrating the obscuring dust layers. Hydrogen gas throughout the galaxy emits characteristic 21 centimeter radiation, allowing astronomers to trace the distribution of neutral atomic hydrogen across vast distances. These radio observations revealed the galaxy's spiral structure and provided the first accurate measurements of galactic rotation. The Doppler shifts of hydrogen emission lines mapped the velocity field of galactic rotation, revealing how different regions orbit the central mass concentration. Infrared observations complement radio studies by detecting the thermal emission from dust grains heated by embedded stars. The 2-micron all-sky survey and subsequent infrared mapping projects constructed detailed charts of stellar distribution, revealing the central bar structure and spiral arms with unprecedented clarity. These observations confirmed theoretical predictions about barred spiral morphology, while revealing asymmetries and substructure within the major spiral arms. The European Space Agency's Gaia mission represents the current pinnacle of galactic cartography. By measuring precise positions and motions of over 1 billion stars, Gaia constructs a three-dimensional map of unprecedented accuracy. The mission's astrometric measurements reveal stellar parallaxes and proper motions, allowing determination of distances and space velocities throughout the local galactic neighborhood. These data transform our understanding of galactic structure from statistical models to direct geometric measurements. Gaia observations reveal the complex kinematic structure of stellar populations, identifying streams of stars with common motions that trace ancient accretion events. The Gaia-Enceladus merger, a major collision that occurred approximately 10 billion years ago, left clear signatures in the phase-space distribution of halo stars. Such discoveries demonstrate how the galaxy assembled through hierarchical merging of smaller stellar systems over cosmic time. The galactic rotation curve, measured through radio astronomy and stellar kinematics, reveals fundamental properties of the galaxy's mass distribution. In the inner regions, rotation velocity increases linearly with radius, indicating solid body rotation characteristic of a centrally concentrated mass distribution. Beyond the solar circle, however, rotation velocity remains approximately constant, rather than declining, as predicted by Kepler's laws. This flat rotation curve provided early evidence for dark matter's existence and continues to constrain models of galaxy formation and evolution. Stellar population studies reveal the galaxy's chemical evolution history. Metal-poor stars in the halo formed from primordial material enriched only by the first generations of massive stars. Disk stars exhibit a clear metallicity gradient, with metal-rich populations concentrated toward the galactic center, where star formation rates remained high throughout cosmic history. The chemical abundance patterns recorded in stellar atmospheres trace the nucleosynthetic contributions of different stellar mass ranges over time. The galaxy's magnetic field structure, mapped through observations of interstellar polarization and synchrotron emission, reveals large-scale organization aligned with spiral arms. This magnetic field influences the dynamics of charged particles in the interstellar medium, while providing additional pressure support against gravitational collapse in star-forming regions. The field's topology suggests generation through dynamo processes operating within the galactic disk. Understanding the Milky Way's structure within the broader context of galaxy evolution reveals our system as a typical large spiral galaxy. Comparative studies of external galaxies provide templates for interpreting observations of our own system, while theoretical models of galaxy formation predict the structural features we observe. The Milky Way's current configuration represents the outcome of over 13 billion years of gravitational assembly, star formation, and chemical evolution. The galaxy continues evolving today through ongoing accretion of satellite galaxies and intergalactic material. The Sagittarius dwarf galaxy currently undergoes tidal disruption, contributing stars to the outer halo while triggering ripples in the galactic disk. These contemporary processes demonstrate that galaxy evolution continues actively rather than representing ancient history frozen in time. Future observations with next-generation telescopes will refine our three-dimensional map of galactic structure while extending measurements to fainter stellar populations. The combination of astrometric, spectroscopic and photometric surveys promises to reveal the complete architecture of our galactic home, transforming our perspective from inhabitants to comprehensive cartographers of this island universe we call the Milky Way. Scattered throughout the spiral arms of our galaxy lie regions of profound cosmic importance. These are not the bright stars that illuminate our night sky, nor the dense stellar clusters that anchor galactic structure. Instead, they appear as dark patches against the star field, seemingly empty voids where light itself has been extinguished. Yet within these apparent absences of illumination, the most fundamental process in galactic evolution unfolds continuously. These regions represent the manufacturing centers of the universe. Within their boundaries, the raw materials of existence undergo transformation into the nuclear furnaces that will power stellar systems for billions of years. The process occurring here connects directly to your own existence, for every atom heavier than hydrogen and helium in your body originated within such a stellar factory during its formation or death. Giant molecular clouds constitute the largest gravitationally bound structures in the galaxy, extending across distances that dwarf individual solar systems. A typical giant molecular cloud spans between 50 and 300 light-years in diameter, containing mass equivalent to between 10,000 and 10 million solar masses. To comprehend this scale, consider that light traveling at 186,000 miles per second requires centuries to traverse these cosmic structures. The temperature within these clouds hovers at approximately 10 to 20 Kelvin, merely degrees above absolute zero. This extreme cold serves a crucial function, allowing hydrogen molecules to maintain their structural integrity rather than dissociating into individual atoms. The density within these regions, while extraordinary by terrestrial standards, remains remarkably sparse by human perception. A cubic centimeter of material within a molecular cloud contains roughly 100 to 1,000 molecules, creating a vacuum superior to any achievable in Earth-based laboratories. Despite this apparent emptiness, these clouds contain sufficient material to construct thousands of stellar systems. The hydrogen and helium within these regions originated during the first 3 minutes following the Big Bang, while heavier elements represent the processed remains of previous stellar generations. Carbon, nitrogen, oxygen, silicon and iron exist as microscopic dust grains, serving as condensation nuclei around which hydrogen molecules accumulate. The transformation from diffuse molecular cloud to concentrated stellar nursery requires the intervention of external forces capable of overcoming the natural tendency of gas to expand. Several mechanisms can trigger this critical transition, each representing a different pathway through which the galaxy manufactures new stars. Density waves propagating through spiral arms compress molecular clouds as they encounter these regions of enhanced gravitational potential. The spiral structure of our galaxy does not rotate as a solid body. Instead, these density waves maintain their pattern, while individual stars and gas clouds move through them at different velocities. When a molecular cloud enters a spiral arm, the increased gravitational field compresses its structure, raising local densities to levels where gravitational collapse becomes inevitable. Shock waves from nearby supernova explosions represent another triggering mechanism. When massive stars reach the end of their evolutionary sequence, they release energy equivalent to 10 billion hydrogen bombs in a single explosive event. These shock waves propagate through the interstellar medium at velocities approaching 10,000 kilometers per second, compressing any molecular clouds in their path. This process creates a feedback cycle where stellar death directly catalyzes stellar birth. Stellar winds from young, massive stars can also excavate cavities within molecular clouds, creating shell-like structures where compressed gas accumulates. These expanding bubbles of hot plasma can trigger star formation in the compressed shells surrounding them, leading to sequential generations of stellar birth radiating outward from the initial formation site. Once gravitational collapse initiates within a molecular cloud, the process accelerates according to the fundamental laws of physics. As the cloud contracts, gravitational potential energy converts to thermal energy, raising the temperature of the collapsing material. Simultaneously, the conservation of angular momentum causes the cloud to rotate more rapidly as it contracts, similar to how a figure skater spins faster when pulling in their arms. This combination of increased temperature and rotation leads to the formation of a flattened rotating disk surrounding a central concentration of matter. The central region, now termed a protostar, continues accumulating material from the surrounding disk through the process of accretion. During this phase, the protostar radiates energy primarily in infrared wavelengths, remaining invisible to optical telescopes, but detectable through specialized instrumentation designed to observe thermal emission. The accretion process generates considerable energy, as gravitational potential energy converts to thermal energy upon impact with the protostellar surface. This energy output can exceed the eventual nuclear luminosity of the mature star, making protostars among the most energetic objects in star-forming regions. The accretion disk surrounding the protostar may extend across hundreds of astronomical units, containing sufficient material to construct multiple planetary systems. Material within the accretion disk experiences varying conditions depending on its distance from the central protostar. Inner regions reach temperatures sufficient to vaporize most solid materials, while outer regions remain cold enough for water, methane, and other compounds to condense into solid particles. This temperature gradient establishes the foundation for the later formation of terrestrial planets in inner regions and gas giants in outer regions of planetary systems. The transition from protostar to main sequence star occurs when the central temperature reaches approximately 10 million Kelvin, the threshold required for hydrogen fusion reactions to commence. At this temperature, the thermal motion of hydrogen nuclei provides sufficient kinetic energy to overcome their mutual electrostatic repulsion, allowing the strong nuclear force to bind them together in fusion reactions. The onset of nuclear fusion marks a fundamental change in stellar behavior. Prior to this moment, the protostar contracted gravitationally, converting potential energy to thermal energy to maintain its structure against further collapse. Once nuclear fusion begins, the star achieves hydrostatic equilibrium, a delicate balance between the outward pressure generated by nuclear reactions and the inward pull of gravitational attraction. This equilibrium condition determines many properties of the mature star, including its luminosity, surface temperature, and evolutionary timescale. Stars with greater mass require higher central temperatures to maintain hydrostatic equilibrium against their stronger gravitational fields, leading to more rapid nuclear burning and shorter lifespans. Conversely, lower mass stars burn their nuclear fuel more slowly, extending their main sequence lifetimes to durations that can exceed the current age of the universe. Located approximately 1,500 light-years from Earth within the constellation Orion, the Orion Nebula provides an exceptional laboratory for studying active star formation. This region represents one of the nearest sites of massive star formation to our solar system, allowing astronomers to observe the stellar birth process in unprecedented detail. The nebula contains approximately 2,000 times the mass of our Sun distributed across a volume roughly 24 light-years in diameter. Within this region, over 3,000 stellar objects have been catalogued, ranging from massive protostars still accumulating material to fully formed main-sequence stars beginning their nuclear burning phase. The diversity of objects within this single region demonstrates the various stages of stellar evolution occurring simultaneously within star-forming environments. 4 massive stars, collectively known as the Trapezium Cluster, dominate the central region of the Orion Nebula. These stars, each containing between 15 and 30 solar masses, generate intense ultraviolet radiation that ionizes the surrounding hydrogen gas, creating the characteristic red emission that makes the nebula visible to optical telescopes. The energy output from these stars exceeds that of our Sun by factors of tens of thousands, illustrating the extreme luminosity achievable by the most massive stellar objects. The trapezium stars formed relatively recently, within the last 1 million years, making them mere infants by stellar standards. Despite their youth, their extreme mass ensures rapid evolution, and they will likely explode as supernovae within the next 10 million years. This rapid evolution demonstrates how the most massive stars serve as both the brightest beacons within star-forming regions and the shortest-lived contributors to galactic chemical evolution. The same accretion disks that feed material onto forming protostars also serve as the construction sites for planetary systems. Within these protoplanetary disks, microscopic dust grains begin a process of gradual accumulation that eventually leads to the formation of asteroids, comets, and planets. The process begins with the collision and sticking of dust particles through electrostatic and van der Waals forces. These initial aggregates, typically measuring micrometers to millimeters in size, continue growing through further collisions until they reach dimensions of several kilometers. At this scale, gravitational attraction becomes significant, accelerating the accretion process and leading to the formation of planetesimals. Planetesimals represent the building blocks of planetary systems, ranging in size from several kilometers to hundreds of kilometers in diameter. Within the inner regions of protoplanetary disks, where temperatures remain high, planetesimals consist primarily of rocky and metallic materials capable of surviving in the intense radiation environment near the central star. These rocky planetesimals serve as the cores around which terrestrial planets accumulate additional material through gravitational attraction. Beyond the snowline, the distance from the central star, where water vapor condenses into solid ice, planetesimals incorporate significant quantities of frozen volatiles. This additional solid material allows planetesimals in outer disk regions to grow more rapidly, eventually reaching masses sufficient to gravitationally capture hydrogen and helium gas from the surrounding disk. This process leads to the formation of gas giant planets whose final masses can exceed that of the central star during the early stages of system evolution. The formation of stars within molecular clouds initiates a process of chemical transformation that fundamentally alters the composition of galactic material. While the initial composition of molecular clouds reflects the cumulative effects of previous stellar generations, the nuclear fusion reactions within newly formed stars continue this process of chemical evolution. During their main sequence lifetimes, stars convert hydrogen into helium through nuclear fusion reactions. This process occurs exclusively within stellar cores, where temperatures and pressures reach levels necessary to overcome the electrostatic repulsion between positively charged atomic nuclei. The helium produced through these reactions accumulates within stellar cores, gradually altering the internal structure and evolution of stars. More massive stars achieve sufficient central temperatures to initiate fusion reactions involving heavier elements. Carbon, nitrogen and oxygen serve as catalysts in the carbon-nitrogen-oxygen cycle, an alternative fusion mechanism that dominates energy production in stars more massive than approximately 1.3 solar masses. These reactions produce trace quantities of heavier elements while maintaining the primary conversion of hydrogen to helium. Stars with masses exceeding approximately 8 solar masses eventually achieve central temperatures sufficient to fuse helium into carbon, carbon into neon and magnesium, and continue through successive fusion stages, producing elements up to iron and nickel. Each fusion stage occurs more rapidly than the previous one, leading to an accelerating pace of nuclear evolution as massive stars approach the end of their main sequence lifetimes. The stellar nurseries scattered throughout our galaxy serve as the primary manufacturing sites for the chemical elements essential to biological processes. While hydrogen and helium originated during the first few minutes following the Big Bang, every heavier element required for life underwent nuclear synthesis within stellar interiors. Carbon, the fundamental building block of organic chemistry, forms through the triple alpha process within helium-burning stellar cores. This reaction requires precise conditions of temperature and density, along with a remarkable quantum mechanical resonance discovered by astronomer Fred Hoyle. Without this specific nuclear property, carbon production would remain negligible, potentially preventing the development of carbon-based life throughout the universe. Oxygen, essential for both biological metabolism and the formation of water molecules, originates through helium fusion reactions that combine carbon nuclei with additional helium nuclei. Nitrogen, required for amino acid and nucleic acid synthesis, forms through carbon-nitrogen-oxygen cycle reactions and through oxygen fusion in more massive stars. These three elements, carbon, nitrogen and oxygen, constitute the foundation of organic chemistry and biological processes. Heavier elements crucial for biological function, including phosphorus, sulfur, calcium and iron, require more extreme nuclear conditions for their synthesis. These elements form primarily within the cores of massive stars during advanced fusion stages or through neutron capture processes occurring during the explosive deaths of massive stars. The distribution of these elements throughout the galaxy depends critically on the efficiency of stellar formation and evolution within molecular clouds. The incorporation of these heavy elements into new stellar systems occurs through their inclusion in the molecular clouds from which subsequent generations of stars form. Each episode of star formation enriches the galactic medium with processed nuclear material, gradually increasing the heavy element content available for planetary system formation. This progressive chemical enrichment explains why stars forming today contain higher abundances of heavy elements than stars that formed during the early history of our galaxy. Within the depths of molecular clouds throughout our galaxy, the process of stellar birth continues according to the fundamental laws of physics established during the first moments of cosmic history. Each new generation of stars represents both an end and a beginning, the culmination of previous stellar evolution, and the initiation of new nuclear processing that will continue for billions of years. The stellar nurseries we observe today contain the raw materials for planetary systems that will not reach maturity for millions of years. Within some of these future worlds, the chemical elements forged in stellar cores may organize into the complex molecular structures capable of supporting life. The carbon in future biological molecules, the oxygen in future atmospheres, and the iron in future planetary cores currently exist as microscopic dust grains within the frigid depths of molecular clouds. This connection between stellar birth and the potential for life represents one of the most profound relationships in cosmic evolution. The same gravitational forces that trigger the collapse of molecular clouds eventually enable the formation of planetary systems where biological processes may emerge. Through this mechanism, stellar nurseries serve not only as the manufacturing sites for stars, but as the ultimate source of the chemical complexity that makes existence itself possible. Stars are not eternal. Despite their seemingly permanent presence in our night sky, every star carries within it the seeds of its own destruction. The very nuclear fusion processes that allow stars to shine for millions or billions of years also determine how they will ultimately meet their end. When we examine stellar death, we discover a fundamental truth about the cosmos. The manner in which a star dies depends entirely on its mass. Stars with masses similar to our Sun, between roughly 0.5 and 8 times the Sun's mass, follow one evolutionary pathway. More massive stars, those exceeding 8 solar masses, follow an entirely different and far more violent trajectory. Low to intermediate mass stars spend the majority of their lives fusing hydrogen into helium in their cores. This process can continue for billions of years, as demonstrated by our own Sun, which has maintained steady hydrogen fusion for approximately 4.6 billion years and will continue this process for another 5 billion years. However, when the hydrogen fuel in the core becomes depleted, these stars begin a complex series of evolutionary changes. The core contracts and heats up, while the outer layers expand dramatically, transforming the star into a red giant. During this phase, the star may grow to hundreds of times its original diameter. Our Sun, when it reaches this stage, will expand beyond the orbit of Mars, likely engulfing Mercury and Venus in the process. The surface temperature drops as the star's energy is distributed across this vastly increased surface area, giving the star its characteristic red coloration. For stars like our Sun, the story ends relatively peacefully. The outer layers are gradually expelled into space, forming what astronomers call a planetary nebula, though these beautiful structures have nothing to do with planets. The name arose from their rounded, planet-like appearance in early telescopes. What remains is the hot, dense core of the original star, now called a white dwarf. This stellar remnant, roughly the size of Earth but containing about 60% of the Sun's original mass, will slowly cool and fade over trillions of years. Massive stars, however, experience a dramatically different fate. These stellar giants burn through their fuel at prodigious rates, living fast and dying young. A star 20 times the mass of the Sun might shine for only 10 million years, a mere instant in cosmic terms. As these massive stars age, they begin fusing heavier and heavier elements in their cores, creating a layered structure resembling an onion. The core fusion proceeds from hydrogen to helium, then to carbon, neon, oxygen, silicon, and finally to iron. Each successive fusion stage releases less energy and occurs more rapidly than the previous one. The final silicon burning phase, which produces iron, may last only a few days. Iron represents the end of the road for nuclear fusion because iron nuclei cannot be fused to release energy. Instead, fusing iron requires energy input. When iron accumulates in the core, the star faces an insurmountable crisis. With no more energy-releasing fusion possible, the core can no longer support itself against its own gravitational collapse. What happens next occurs with breathtaking speed. The iron core, approximately the size of Earth, but containing more mass than our Sun, collapses from a diameter of thousands of kilometers to merely 20 kilometers in less than a second. This collapse compresses matter to densities that exceed those found in atomic nuclei. Protons and electrons are crushed together to form neutrons, releasing vast numbers of neutrinos in the process. The core becomes so dense that a teaspoon of its material would weigh as much as Mount Everest. When the collapsing material rebounds off this incredibly dense neutron core, it creates a shock wave that propagates outward through the star's layers. The resulting supernova explosion releases more energy in seconds than our Sun will produce over its entire 10 billion year lifetime. The explosion is so luminous that it can briefly outshine an entire galaxy containing hundreds of billions of stars. For weeks or months, a single supernova can be visible from billions of light years away, appearing as a new star in the sky to distant observers. The death of massive stars represents one of the most important processes in galactic evolution. Supernovae serve as the primary mechanism by which heavy elements created in stellar cores are distributed throughout the galaxy. Without these explosive events, the universe would consist almost entirely of hydrogen and helium, the primordial elements created during the Big Bang. During their lifetimes, massive stars synthesize carbon, oxygen, silicon, iron, and dozens of other elements through nuclear fusion. However, these elements remain trapped within the star until the supernova explosion disperses them into the surrounding interstellar medium. The explosion accelerates this enriched material to velocities of thousands of kilometers per second, creating expanding shells of hot gas and dust that can influence star formation across vast regions of the galaxy. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were forged in the nuclear furnaces of massive stars and scattered into space by supernova explosions. Carl Sagan's famous assertion that we are made of starstuff refers specifically to this process of stellar nucleosynthesis and subsequent dispersal through supernova. The enrichment of the interstellar medium with heavy elements has profound consequences for future generations of stars and planets. Early in the universe's history, stars could only form from hydrogen and helium, limiting their ability to develop planetary systems capable of supporting complex chemistry. As successive generations of massive stars lived and died, they gradually enriched the galaxy with heavier elements, eventually enabling the formation of rocky planets like Earth. This process of cosmic recycling operates on timescales of millions to billions of years. Gas clouds enriched by ancient supernovae collapse to form new stars, some of which are massive enough to eventually explode themselves, further enriching the interstellar medium. Each cycle increases the heavy element content, or metallicity, of the galaxy. Our Sun, as a relatively young star formed 4.6 billion years ago, contains approximately 1.3% heavy elements by mass, a composition that made possible the formation of the terrestrial planets in our solar system. Lower mass stars also contribute to cosmic recycling, though through gentler mechanisms. When Sun-like stars evolve into red giants, they develop powerful stellar winds that carry away substantial portions of their mass. These winds transport elements created in the star's interior, particularly carbon and nitrogen, into the surrounding space. When the star finally sheds its outer layers to form a planetary nebula, these elements are distributed into the interstellar medium. The beautiful planetary nebulae we observe throughout the galaxy represent snapshots of this gentler recycling process. The Ring Nebula in Lyra, the Helix Nebula in Aquarius, and thousands of similar structures mark the locations where Sun-like stars have contributed their processed material to the galactic ecosystem. While less dramatic than supernovae, these events collectively process enormous quantities of material over cosmic time. The aftermath of stellar death produces some of the most extreme objects in the universe. The specific nature of these stellar remnants depends on the original mass of the progenitor star, leading to a fascinating menagerie of exotic objects that challenge our understanding of physics. White dwarf stars represent the most common stellar endpoint, formed when stars with initial masses between approximately 0.5 and 8 solar masses exhaust their nuclear fuel. These objects pack roughly 60% of the Sun's mass into a sphere no larger than Earth. The matter within a white dwarf exists in a state unknown on Earth, supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state. White dwarfs are born extremely hot, with surface temperatures exceeding 100,000 Kelvin, but they lack internal energy sources and gradually cool over billions of years. The Chandrasekhar limit, approximately 1.4 solar masses, represents the maximum mass a white dwarf can support. If additional matter accumulates on a white dwarf surface, either through accretion from a companion star or a direct collision with another white dwarf, it may exceed this limit and undergo a thermonuclear explosion called a Type Ia supernova. These thermonuclear supernovae serve as standard candles for measuring cosmic distances because they release nearly identical amounts of energy. Their uniform brightness allows astronomers to determine accurate distances to remote galaxies, observations that led to the discovery of dark energy and the accelerating expansion of the universe. Neutron stars form when the cores of massive stars, typically between 8 and 25 solar masses, collapse during supernova explosions. The extreme pressures during core collapse overcome electron degeneracy pressure, forcing protons and electrons to combine into neutrons. The resulting neutron star contains approximately 1.4 to 2.0 solar masses, compressed into a sphere only 20 kilometers in diameter. The density of neutron star matter approaches that found in atomic nuclei, roughly 100 million tons per cubic centimeter. A sugar cube-sized piece of neutron star material would weigh about the same as Mount Everest. This extreme density creates equally extreme gravitational fields, with surface gravity approximately 200 billion times stronger than Earth's. Neutron stars possess magnetic fields trillions of times stronger than Earth's magnetic field. As they rotate, these magnetic fields accelerate charged particles to tremendous speeds, producing beams of radiation that sweep across space like lighthouse beams. When these beams align with Earth, we observe pulsars, rapidly rotating neutron stars that appear to pulse with clockwork regularity. The most precisely timed pulsars keep better time than atomic clocks, with rotation periods stable to 1 part in a billion. The Crab pulsar, formed in the supernova observed by Chinese astronomers in 1054 CE, rotates 30 times per second and has been gradually slowing down as it loses rotational energy through electromagnetic radiation. Black holes represent the ultimate stellar endpoint, formed when the cores of the most massive stars, those exceeding approximately 25 to 30 solar masses, collapse beyond the neutron degeneracy pressure limit. No known force can halt the gravitational collapse of such massive cores, leading to the formation of objects so dense that not even light can escape their gravitational influence. Stellar mass black holes typically range from 3 to 50 times the mass of the Sun, though recent gravitational wave detections have revealed black holes with masses exceeding 100 solar masses. These objects fundamentally alter the structure of space-time in their vicinity, creating regions where the normal rules of physics break down. The event horizon marks the boundary beyond which nothing can escape a black hole's gravitational pull. For a black hole with the mass of our Sun, the event horizon would have a radius of approximately 3 kilometers. The gravitational time dilation near a black hole is so extreme that an outside observer would see time slow to a crawl for anything approaching the event horizon. Despite their reputation for consuming everything in their vicinity, isolated black holes are actually quite difficult to detect because they emit no light. Astronomers typically identify stellar mass black holes by observing their gravitational effects on companion stars in binary systems. Material spiraling into a black hole forms an accretion disk that can reach temperatures of millions of degrees, producing intense X-ray emission the telescopes can detect across vast distances. These exotic remnants, white dwarfs, neutron stars and black holes, represent the final chapter in the lives of individual stars, but they also play crucial roles in the ongoing evolution of the galaxy. White dwarfs serve as archaeological records of past stellar populations, while neutron stars and black holes can dramatically influence their surroundings through powerful magnetic fields, gravitational effects, and high-energy radiation. The distribution and properties of these stellar remnants provide important clues about the history of star formation in the Milky Way. Globular clusters, ancient collections of stars formed early in the galaxy's history, contain numerous white dwarfs that help astronomers determine the age and chemical evolution of our galaxy. Meanwhile, the locations and velocities of neutron stars and black holes carry information about the supernova explosions that created them, sometimes revealing evidence of asymmetric explosions that can accelerate these objects to high velocities through space. As we survey the stellar graveyard scattered throughout our galaxy, we observe not destruction, but transformation. The death of stars creates the raw materials for new generations of stars and planets, while the exotic objects left behind continue to shape the galactic environment through their extreme physics. These stellar cataclysms represent not endings but essential phases in the ongoing cycle of cosmic evolution that connects the first stars to the complex chemistry required for life itself. At the center of our galaxy lies an object so dense that it warps space-time itself into a funnel of no return. This gravitational titan, invisible to our eyes yet commanding the orbits of stars across thousands of light years, represents one of the most extreme environments in the known universe. What we have discovered at the Milky Way's core challenges our understanding of physics itself and reveals the dark engine that has shaped our cosmic home for over 13 billion years. 26,000 light-years from Earth, beyond the constellation Sagittarius, radio telescopes detect powerful emissions from a source no larger than our solar system. This compact region, designated Sagittarius A star or SCAR A star, harbours a mass 4 million times greater than our Sun, compressed into a sphere just 12 million miles across. To comprehend this density, consider that if Earth possessed the same mass-to-size ratio, our entire planet would compress to the dimensions of a marble, yet retain all its gravitational influence. The evidence for this cosmic leviathan emerged gradually through decades of patient observation. Astronomers tracking individual stars near the galactic center witnessed something unprecedented. Massive stellar giants following elliptical paths at velocities reaching 5,000 kilometers per second. These stars, each containing dozens of times our Sun's mass, traced orbits around an apparently empty point in space with mathematical precision. The gravitational choreography demanded an explanation that only one phenomenon could provide: a supermassive black hole. In 2020, the Event Horizon Telescope achieved what many considered impossible. This planet-spanning array of radio dishes operating in perfect synchronization captured the first direct image of Sagittarius A star's shadow. The resulting photograph revealed a glowing ring of superheated matter surrounding a dark central void, the photon sphere, where light itself orbits the black hole before either escaping to infinity or spiraling inward beyond the event horizon. This image confirmed what mathematical models had predicted. We were observing the silhouette of warped space-time itself. The physics governing Sagittarius A star operates in a realm where Einstein's general relativity becomes essential for accurate description. Within the innermost stable circular orbit, approximately 6 times the event horizon radius, matter cannot maintain stable trajectories. Gas and debris spiraling inward form an accretion disk, heating to temperatures exceeding 10 million degrees Celsius through friction and magnetic field interactions. This superheated plasma emits radiation across the electromagnetic spectrum, from radio waves to X-rays, creating the observational signature that betrays the black hole's presence. Unlike its more active galactic cousins, Sagittarius A star remains relatively quiescent, consuming material at a rate of only 1 Earth mass per year. This modest appetite stands in stark contrast to the voracious supermassive black holes powering quasars and active galactic nuclei, which can devour hundreds of solar masses annually. Our galaxy's central black hole occasionally flares to hundreds of times its normal luminosity when gas clouds or stellar material venture too close, but these outbursts last mere hours before subsiding to typical levels. The formation of such a massive compact object presents one of astrophysics' most compelling puzzles. Traditional stellar evolution cannot produce black holes exceeding approximately 50 solar masses through direct collapse. Yet Sagittarius A star contains the equivalent mass of 4 million stars. 3 primary theories attempt to explain this cosmic giant's origin. The first proposes that intermediate mass black holes, themselves formed from the first generation of massive stars in the early universe, grew through successive mergers and accretion over billions of years. The second mechanism involves direct collapse of primordial gas clouds in the young universe. During the epoch of first galaxy formation, when the cosmos was denser and hotter than today, massive gas reservoirs could potentially collapse directly into black holes without first forming stars. These seed black holes would then grow alongside their host galaxies, fed by the continuous infall of surrounding material. The third possibility suggests that dense stellar clusters in the galactic center underwent runaway collisions, forming successively more massive objects until gravitational collapse became inevitable. Computer simulations demonstrate that in sufficiently dense environments, stellar collisions can produce objects massive enough to collapse directly into intermediate mass black holes, which then serve as seeds for further growth. Regardless of its formation mechanism, Sagittarius A* has profoundly influenced our galaxy's evolution. The black hole's gravitational influence extends throughout the galactic bulge, affecting stellar orbits across thousands of light-years. Periodic outbursts from the accretion disk likely regulated star formation in the inner galaxy by heating surrounding gas and preventing its collapse into new stellar generations. This feedback mechanism helps explain why massive galaxies like the Milky Way ceased forming stars as prolifically as they did during their youth. The immediate vicinity of Sagittarius A* represents an extreme laboratory for testing fundamental physics. Within the innermost few light-years, stellar densities reach millions of times higher than in our solar neighborhood. Ancient red giant stars, their outer atmospheres stripped away by tidal forces, orbit the black hole as compact helium cores. More exotic objects likely populate this region as well: neutron stars, white dwarfs, and possibly intermediate mass black holes, all following intricate gravitational dances around the central mass. General relativity predicts several phenomena observable only in such extreme gravitational environments. Frame dragging effects caused by the black hole's rotation twist space-time itself and drag nearby objects along with the spinning geometry. Gravitational redshift, the stretching of light climbing out of deep gravitational wells, becomes dramatically apparent as photons lose energy escaping the black hole's vicinity. These relativistic effects provide unique opportunities to test Einstein's theory under conditions impossible to replicate elsewhere. Recent observations have detected what appear to be stars in the final phases before crossing the event horizon. These objects, exhibiting extreme gravitational redshift and time dilation effects, offer unprecedented glimpses into the physics of extreme space-time curvature. As these stars approach their inevitable fate, they provide real-time laboratories for studying the boundary between classical physics and the quantum realm. The black hole's influence extends beyond its immediate gravitational domain through powerful outflows and magnetic field interactions. Charged particles accelerated near the event horizon generate relativistic jets, narrow beams of matter and energy that can extend thousands of light-years into intergalactic space. While Sagittarius A*'s jets remain relatively weak compared to those produced by more active, supermassive black holes, they still carry significant energy and momentum, potentially influencing gas dynamics throughout the inner galaxy. Current observations suggest that our galaxy's central black hole may be preparing for increased activity. The approaching gas cloud known as G2, with a mass roughly 3 times that of Earth, is predicted to pass within a few 100 billion kilometers of Sagittarius A*. While initial encounters in 2014 produced less dramatic results than anticipated, continued monitoring may reveal enhanced accretion and emission as gravitational tides stretch and heat the infalling material. Understanding Sagittarius A* provides crucial insights into the relationship between supermassive black holes and their host galaxies. Observations across the universe reveal a tight correlation between central black hole mass and the velocity dispersion of stars in galactic bulges. This relationship, known as the M-sigma relation, suggests that black holes and galaxies evolve together through processes that remain poorly understood. Our galaxy's central black hole serves as the nearest example of this cosmic symbiosis, offering detailed observations impossible to achieve in more distant systems. The story of Sagittarius A* continues unfolding as new technologies provide unprecedented detail about our galaxy's dark heart. Future observations with next-generation telescopes promise to resolve the event horizon structure more clearly, potentially detecting the predicted photon ring, a series of increasingly narrow rings caused by photons orbiting the black hole multiple times before escaping. These observations will test general relativity's predictions in the strongest gravitational fields accessible to human observation, pushing our understanding of space-time itself to its theoretical limits. The supermassive black hole at our galaxy's center holds within its gravitational grip the secrets of cosmic evolution spanning 13.8 billion years. To understand how Sagittarius A star achieved its tremendous mass of 4 million suns, we must rewind time itself to the universe's infancy, when the first atoms formed in the cooling aftermath of creation. In those primordial moments following the Big Bang, the universe existed as a nearly uniform sea of hydrogen and helium. Temperature fluctuations measuring mere millionths of a degree would determine the architecture of everything that followed. These quantum ripples, imprinted in the cosmic microwave background radiation, served as gravitational seeds that would eventually collapse into the first stars, galaxies, and the massive black holes that anchor them. The earliest stellar populations ignited approximately 100 million years after the Big Bang, during what astronomers term the cosmic dawn. These population 3 stars differed fundamentally from modern stellar objects. Composed entirely of primordial hydrogen and helium, they achieved masses exceeding 100 times that of our Sun. Their nuclear furnaces burned with extraordinary intensity, consuming their fuel reserves in mere millions of years before collapsing into black holes with masses ranging from tens to hundreds of solar masses. These primordial black holes became the gravitational anchors around which the first protogalaxies assembled. Dark matter halos, invisible scaffolding comprising 85% of all matter, provided the structural framework necessary for ordinary matter to accumulate. Within these dark matter wells, successive generations of star formation commenced, each cycle enriching the cosmic medium with heavier elements forged in stellar cores. The Milky Way's formation history reveals itself through galactic archaeology, a discipline that reconstructs ancient events by analyzing the chemical compositions and orbital characteristics of surviving stellar populations. The oldest stars in our galaxy's halo contain chemical signatures indicating formation from nearly pristine primordial gas. These stellar fossils preserve evidence of the galaxy's chaotic youth, when smaller building blocks merged through violent gravitational encounters. Computer simulations demonstrate that massive galaxies like the Milky Way assembled through hierarchical merging processes. Smaller dark matter halos, each containing their own stellar populations, gradually coalesced through gravitational attraction. Each merger event added mass to the central black hole, while simultaneously disrupting existing stellar orbits and triggering intense bursts of star formation from compressed gas clouds. The lambda cold dark matter model predicts that our galaxy consumed dozens of satellite systems throughout its evolutionary history. Evidence for these ancient cannibalistic events persists in the form of stellar streams, coherent groups of stars sharing common orbital properties that trace the disrupted remains of accreted dwarf galaxies. The Sagittarius stream represents one such tidal remnant stretching completely around the galactic disk as testimony to our galaxy's gravitational appetite. Approximately 10 billion years ago, a fundamental transition occurred in the Milky Way's structural evolution. The chaotic merging phase gave way to more quiescent accretion, allowing the formation of a stable rotating disk. Gas settling into this disk became the raw material for subsequent generations of star formation, including the birth of our Sun 4.6 billion years ago. The galactic disk's formation coincided with the establishment of spiral density waves, compression patterns that propagate through the stellar medium like ripples on a cosmic pond. These waves concentrate gas and dust, triggering star formation in the characteristic spiral arm patterns that define our galaxy's architecture. The spiral structure serves as a self-regulating mechanism, processing interstellar medium into stars, while simultaneously replenishing the gas supply through stellar winds and supernova explosions. Chemical evolution models reveal how successive generations of stars enriched the galactic medium with heavier elements essential for planet formation and ultimately biological processes. The first stars produced primarily carbon, oxygen, and silicon through nucleosynthesis. Later generations added iron peak elements through Type Ia supernova explosions, creating the chemical complexity necessary for terrestrial planet formation. Our Sun represents a relatively late arrival in galactic terms, forming when the Milky Way had already synthesized sufficient heavy elements to enable rocky planet formation. The solar system's location in the Orion Cygnus arm places us in what galactic habitability researchers term the galactic habitable zone, a region where stellar metallicity supports planet formation while avoiding the intense radiation environment near the galactic center. The James Webb Space Telescope now allows astronomers to observe galaxy formation processes in unprecedented detail, revealing how supermassive black holes and their host galaxies co-evolved through cosmic time. These observations confirm that black hole growth correlates strongly with the stellar mass of galactic bulges, suggesting fundamental connections between central black holes and the star formation histories of their host systems. Modern measurements indicate that Sagittarius A star likely achieved most of its current mass through a combination of gas accretion and black hole mergers during the galaxy's assembly phase. Each merger event between proto-galactic fragments would have brought together their respective central black holes, eventually resulting in gravitational wave-emitting coalescence events that added mass to the growing central object. The Milky Way's current state represents a mature spiral galaxy in which star formation proceeds at a relatively modest rate of approximately 2 solar masses per year. This quiescent phase will persist for several billion years before the anticipated merger with the Andromeda Galaxy initiates another period of enhanced stellar birth and black hole growth. Understanding galactic formation processes provides crucial context for assessing the likelihood of life elsewhere in the universe. The complex sequence of events required to create chemically enriched, gravitationally stable environments suitable for biological evolution may represent one of the key filters determining the abundance of life-bearing worlds throughout cosmic history. The Milky Way does not exist in isolation. Suspended in the cosmic void, our galaxy finds itself bound to a collection of gravitational companions that form what astronomers call the local group. This gravitationally bound association contains over 50 galaxies, each following orbital trajectories around a common gravitational center located roughly between our own Milky Way and its most significant neighbor, the Andromeda Galaxy. Understanding the local group requires us to appreciate the fundamental nature of galactic clustering. In the universe, galaxies rarely exist as solitary islands. Instead, they congregate in hierarchical structures, from small groups containing just a few members to massive galaxy clusters housing thousands of individual systems. The local group represents an intermediate structure, a moderately sized galactic association spanning approximately 10 million light-years across. Within this cosmic neighborhood, two massive spiral galaxies dominate the gravitational landscape. The Milky Way, containing roughly 400 billion stars, stands as one heavyweight. The Andromeda Galaxy, designated M31 in astronomical catalogues, serves as the other. At approximately 1 trillion stars, Andromeda holds the distinction of being the most massive galaxy in our local assembly. These two spiral giants, separated by 2.5 million light-years, contain the vast majority of mass and stellar populations within the entire local group. The third largest member, the Triangulum Galaxy, or M33, contributes significantly less mass than its spiral cousins. This galaxy contains approximately 40 billion stars and maintains a complex gravitational relationship with both the Milky Way and Andromeda. Current observations suggest Triangulum may be gravitationally bound to Andromeda, orbiting the larger galaxy at a distance that varies over cosmic time. Beyond these three major players, dozens of dwarf galaxies populate the local group. These smaller systems, containing anywhere from millions to billions of stars, serve as crucial laboratories for understanding galaxy formation and evolution. Many of these dwarf galaxies exist as satellites to the larger spirals, trapped in gravitational wells that slowly strip away their outer stellar populations through tidal forces. The large and small Magellanic Clouds represent the most prominent satellite galaxies of the Milky Way. Visible from the southern hemisphere, these irregular dwarf galaxies maintain a complex orbital dance around our galaxy. The large Magellanic Cloud, positioned approximately 160,000 light-years from the Milky Way's center, contains roughly 30 billion stars organized in a somewhat chaotic structure, lacking the ordered spiral arms of larger galaxies. The small Magellanic Cloud, more distant at 200,000 light-years, houses approximately 7 billion stars. Both Magellanic systems show clear evidence of gravitational disruption caused by their close passage to the Milky Way. Streams of hydrogen gas, collectively known as the Magellanic Stream, trail behind these galaxies like cosmic wake turbulence, extending across more than 100 degrees of sky when viewed from Earth. Andromeda possesses its own retinue of satellite galaxies, including M32 and M110, both elliptical systems that likely formed through different evolutionary pathways than the dwarf spheroidal satellites common around the Milky Way. These Andromedan companions provide insights into how different types of massive galaxies accumulate and maintain their satellite populations over cosmic time. The gravitational interactions within the local group create a complex choreography of orbital motion. Each galaxy follows a trajectory influenced not only by the two dominant spiral systems, but also by the collective gravitational field of all group members. Computer simulations reveal that many of the smaller galaxies follow highly elliptical orbits, approaching and receding from the massive galaxies over timescales measured in billions of years. These gravitational encounters leave observable signatures in the form of stellar streams and tidal tails. When a smaller galaxy passes close to a larger one, differential gravitational forces stretch the smaller system, pulling stars away from the galactic core and distributing them along the orbital path. Astronomers have detected numerous such streams around both the Milky Way and Andromeda, providing forensic evidence of past gravitational interactions. The local group's most significant gravitational story centers on the approaching collision between the Milky Way and Andromeda. Current measurements indicate these two galaxies are approaching each other at approximately 110 kilometers per second. At this rate, the first close passage will occur in roughly 4.5 billion years, initiating a complex merger process that will ultimately combine both systems into a single, larger galaxy. This impending collision represents more than a simple merger of stellar populations. When two massive spirals interact gravitationally, the process triggers dramatic changes in star formation rates, stellar orbits, and galactic structure. Gas clouds within both galaxies will collide and compress, igniting bursts of new star formation that may temporarily increase the combined system's luminosity by several orders of magnitude. The gravitational disruption will fundamentally alter the orbital characteristics of billions of stars. Computer models suggest that during the merger process, some stars will be flung into intergalactic space, ejected from the combined system entirely. Others will find themselves in highly eccentric orbits that carry them far from the merged galaxy's center before returning in long, looping trajectories. Our solar system's fate during this cosmic collision remains uncertain but statistically predictable. The vast spaces between individual stars mean that direct stellar collisions remain extremely unlikely. However, the Sun's orbit around the galactic center will almost certainly change dramatically. Models suggest our solar system has roughly equal chances of ending up in the outer regions of the merged galaxy, or being ejected into the space between galaxies. The merger product, informally dubbed Milky by astronomers, will likely resemble a giant elliptical galaxy rather than maintaining the spiral structure of its progenitors. Elliptical galaxies typically form through major mergers between spiral systems, and the Milky Way Andromeda collision fits this pattern perfectly. The resulting system will contain approximately 1.4 trillion stars distributed in a roughly spherical or elliptical configuration. Understanding the local group's dynamics requires appreciating the role of dark matter in galactic interactions. Each galaxy exists within an extensive halo of invisible matter that outweighs the visible stars by ratios of 10:1 or more. These dark matter halos extend far beyond the visible boundaries of each galaxy, creating gravitational influence zones that can span millions of light-years. The distribution of dark matter within the local group determines the overall gravitational field that guides galactic motions. While we cannot observe dark matter directly, its gravitational effects become apparent through the orbital velocities of group members and the large-scale structure of stellar streams and tidal features. How? Recent observations have revealed that the local group itself moves through space as a coherent unit. We are falling toward the Virgo cluster, a much larger galactic association containing thousands of galaxies located approximately 65 million light-years away. This motion reflects the hierarchical nature of cosmic structure, where smaller groups like ours exist as components of progressively larger gravitational systems. The local group's position within the broader cosmic web influences its internal dynamics and evolutionary trajectory. Surrounded by vast voids containing few galaxies, our galactic neighborhood represents a moderately dense region where matter has successfully collapsed into bound structures. This environment has remained relatively stable over cosmic time, allowing the complex gravitational relationships within the group to develop and persist. The study of local group dynamics provides crucial insights into galaxy formation theories. The observed properties of dwarf satellites, their spatial distribution around massive galaxies, and their star formation histories all serve as tests for cosmological models describing how structure formed in the early universe. Discrepancies between theoretical predictions and observed satellite properties continue to drive refinements in our understanding of galaxy formation physics. As we observe the local group today, we witness a gravitational system in transition. The approaching merger between the Milky Way and Andromeda will fundamentally reorganize this cosmic neighborhood, eliminating the current two-galaxy dominance and creating a single, massive system surrounded by disrupted satellite populations. This transformation represents a natural step in the hierarchical assembly of cosmic structure, where smaller units combine to form progressively larger systems over cosmic time. The local group serves as our immediate cosmic environment, the gravitational context within which our galaxy has evolved and will continue to change. By understanding these neighboring systems and their mutual interactions, we gain perspective on our galaxy's place in the larger cosmic story and insight into the fundamental processes that shape the universe on the largest scales. Among the countless stellar furnaces scattered throughout our galaxy's spiral arms, there exists a profound mystery that challenges our understanding of life itself. Within the span of just 3 decades, we have discovered that planets are not rare cosmic accidents, but rather common companions to the stars that illuminate our galaxy. This revelation has fundamentally transformed our perspective on one of humanity's most enduring questions: are we alone in the universe? The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary systems by monitoring over 150,000 stars simultaneously. Through the precise measurement of stellar brightness variations caused by planets transiting across their host stars, Kepler revealed that approximately 1 in every 5 Sun-like stars hosts an Earth-sized planet within the habitable zone. When we extrapolate this ratio across the Milky Way's estimated 400 billion stars, the implications become staggering. Our galaxy may harbor tens of billions of potentially habitable worlds. The technique of transit photometry, employed by Kepler and its successor TESS, represents one of the most elegant methods of planetary detection ever devised. When a planet passes between its star and our telescopes, it blocks a minute fraction of the star's light, creating a characteristic dimming pattern that reveals not only the planet's existence but also its size, orbital period, and distance from its host star. The precision required for these measurements is extraordinary. Detecting an Earth-sized planet around a Sun-like star requires measuring brightness changes of just 84 parts per million, equivalent to detecting the dimming caused by a single ant crawling across a car headlight viewed from several miles away. Within this vast catalogue of exoplanets lies a subset of worlds that occupy the most intriguing real estate in the galaxy. The habitable zone, or as astronomers colloquially term it, the Goldilocks zone. This region around each star represents the orbital distance where liquid water can exist on a planet's surface, neither boiling away as on Venus nor freezing solid as on Mars. The boundaries of this zone depend critically on the star's temperature and luminosity, creating a complex 3-dimensional map of habitability throughout our galaxy. Consider the diversity of stellar environments that could support life. Red dwarf stars, which comprise roughly 75% of all stars in the Milky Way, burn their nuclear fuel so slowly that they can maintain stable energy output for trillions of years. A planet orbiting within the habitable zone of a red dwarf would experience constant daylight on one hemisphere and eternal darkness on the other, creating extreme temperature gradients that could drive powerful atmospheric circulation patterns. Recent atmospheric modeling suggests that such tidally locked worlds might indeed maintain liquid water, particularly if they possess substantial atmospheres capable of redistributing heat from the day side to the night side. The atmospheric composition of these distant worlds holds the key to understanding their potential for habitability. Water vapor, carbon dioxide and methane create greenhouse effects that can extend the habitable zone outward from a star, while reflective clouds and ice can push it inward. The James Webb Space Telescope has begun the painstaking process of analyzing exoplanet atmospheres through transmission spectroscopy, a technique that examines how starlight filters through a planet's atmosphere during transit. Each molecular species absorbs light at characteristic wavelengths, creating spectroscopic fingerprints that reveal the chemical composition of these alien worlds. The search for biosignatures, chemical indicators of life's presence, represents perhaps the most ambitious scientific endeavor of our time. Oxygen, when detected in combination with water vapor, could indicate photosynthetic life similar to that which transformed Earth's atmosphere billions of years ago. Methane, in the absence of obvious geological sources, might signal biological processes. More exotic biosignatures could include industrial pollutants in the atmospheres of technologically advanced civilizations, or even the artificial lights illuminating the night sides of inhabited worlds. Yet the detection of life elsewhere in the galaxy faces formidable challenges. The nearest potentially habitable exoplanet, Proxima Centauri b, orbits a red dwarf star just 4.2 light-years away. Despite this relatively close proximity, current technology cannot resolve surface features or definitively characterize its atmosphere. The planet's host star, Proxima Centauri, regularly unleashes powerful stellar flares that could strip away atmospheric gases, making long-term habitability questionable. The concept of the galactic habitable zone adds another layer of complexity to our search for life. This theoretical region, sometimes called the Galactic Goldilocks zone, represents the range of distances from the Milky Way's center where conditions might be most favorable for the development and persistence of life. Too close to the galactic center, and planets face increased radiation from stellar explosions and disruption from gravitational interactions. Too far from the center, and stars may lack the heavy elements necessary to form rocky planets and support complex chemistry. Our solar system occupies a position roughly halfway out from the galactic center in what appears to be an optimal location for habitability. The abundance of heavy elements in our region of the galaxy enabled the formation of rocky planets like Earth, while our distance from the chaotic galactic center protected us from the most extreme cosmic violence. This galactic perspective suggests that the distribution of life in the Milky Way may not be uniform, but concentrated in specific regions where stellar metallicity and gravitational stability create favorable conditions. The timeline of cosmic evolution adds yet another constraint to the emergence of life. The first generation of stars, formed from the primordial hydrogen and helium created in the Big Bang, contained virtually no heavy elements. Only after these massive stars lived their brief lives and exploded as supernovae did the galaxy become enriched with carbon, oxygen, silicon and iron, the essential building blocks of rocky planets and organic chemistry. This process of stellar nucleosynthesis and galactic chemical evolution means that the universe needed several billion years to become capable of supporting Earth-like worlds. The habitable age of the universe extends far into the future. Red dwarf stars will continue burning for trillions of years, potentially providing stable energy sources for life long after our sun has exhausted its nuclear fuel. Even as star formation gradually declines and the galaxy's stellar population ages, existing planetary systems may continue to support life for timescales that dwarf the current age of the universe. This temporal perspective suggests that if life exists elsewhere in the Milky Way, it may be far older and potentially more advanced than life on Earth. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating extraterrestrial civilizations in our galaxy. While many of its terms remain poorly constrained, recent exoplanet discoveries have begun to provide observational data for several factors. The fraction of stars with planets appears to be close to 1, meaning that planetary systems are the norm rather than the exception. The number of potentially habitable planets per system averages around 1 for Sun-like stars, though this number may be higher for longer-lived red dwarf systems. The most uncertain terms in the Drake equation involve the probability that life will arise on a habitable planet and the likelihood that such life will develop intelligence and technology. On Earth, life appeared remarkably quickly after the planet became habitable, suggesting that the transition from chemistry to biology may be relatively straightforward given appropriate conditions. However, the evolution of complex multicellular life took billions of years, and the development of intelligence and technology appears to be a rare and recent phenomenon in Earth's history. The Fermi paradox, named after physicist Enrico Fermi, highlights the apparent contradiction between the high probability of extraterrestrial life and the complete absence of evidence for such life. Given the vast number of potentially habitable worlds in our galaxy and the billions of years available for evolution, where is everybody? Various solutions to this paradox have been proposed, ranging from the possibility that Earth is truly unique in hosting life, to the idea that advanced civilizations inevitably destroy themselves or transcend physical existence. Recent research has identified several factors that may make Earth-like conditions rarer than initially assumed. The presence of a large moon, which stabilizes Earth's axial tilt and creates tides that may have aided the transition of life from sea to land, appears to be uncommon among exoplanets. The configuration of our solar system, with massive gas giants like Jupiter acting as gravitational shields that protect the inner planets from cometary bombardment, may also be atypical. The concept of planetary habitability continues to evolve as we discover life thriving in increasingly extreme environments on Earth. Organisms have been found living in boiling hot springs, highly acidic waters, deep underground rock formations, and even within the radioactive cores of nuclear reactors. These extremophiles expand our definition of habitability and suggest that life might persist under conditions previously thought impossible. The search for extraterrestrial life operates on multiple fronts simultaneously. Radio telescopes scan the galaxy for artificial signals that might indicate the presence of technological civilizations. The search for extraterrestrial intelligence, or SETI, has monitored billions of star systems over several decades, though the vastness of parameter space means that even negative results provide little constraint on the existence of alien civilizations. Future missions will bring unprecedented capabilities to the search for life beyond Earth. The Roman Space Telescope will conduct a comprehensive survey of exoplanets using gravitational microlensing, a technique sensitive to Earth-mass planets at Earth-like distances from their stars. Ground-based, extremely large telescopes, with mirrors spanning 25 to 40 meters in diameter, will possess the resolution and sensitivity needed to directly image nearby exoplanets and analyze their atmospheric compositions in detail. The implications of discovering life elsewhere in the galaxy extend far beyond astronomy. Such a discovery would represent the most profound paradigm shift in human understanding since the Copernican revolution removed Earth from the center of the universe. It would confirm that the biological processes that gave rise to consciousness are not unique to our world, but represent fundamental properties of matter and energy under appropriate conditions. Until such a discovery is made, We remain alone in the observable universe, the only known example of matter organized in such complexity that it can contemplate its own existence. The search for life among the stars continues, driven by our deepest questions about our place in the cosmos and the nature of consciousness itself. In the silent darkness between the stars, other worlds may harbor their own observers, gazing up at their own night skies and wondering, as we do, whether they are alone in the vast cathedral of space and time. The Milky Way galaxy appears serene from our terrestrial perspective, a gentle arc of starlight spanning the night sky. This tranquil appearance masks a fundamental truth that astronomers have spent decades uncovering. Our galaxy operates as a cosmic shooting gallery, where invisible forces and catastrophic events regularly reshape entire stellar neighborhoods. The question that haunts astrobiologists worldwide is not whether these dangers exist, but how any life survives them at all. Every second that passes, high-energy particles stream through your body at nearly the speed of light. Somewhere in the galactic disk, a star explodes with the energy of 10 billion suns. Radio waves from colliding neutron stars wash over Earth, carrying signals from gravitational catastrophes that occurred millions of years ago. These phenomena represent just the beginning of a cosmic threat assessment that reveals how precarious our existence truly is. When stars 8 times more massive than our Sun exhaust their nuclear fuel, they face an inevitable gravitational collapse. This process occurs within milliseconds, compressing matter to densities that exceed atomic nuclei. The resulting core bounce generates a shock wave that tears through the stellar envelope at speeds exceeding 30,000 kilometers per second. What emerges is a supernova, an explosion so energetic that for weeks a single dying star can outshine the combined luminosity of every other star in the galaxy. The electromagnetic radiation from these explosions travels in all directions, creating expanding spheres of deadly energy. At distances within 50 light-years, a supernova releases enough high-energy photons to strip away a planet's ozone layer completely. Without this protective shield, ultraviolet radiation from the star would sterilize the surface, destroying the complex organic molecules essential for life as we know it. Geological evidence suggests that supernovae have influenced Earth's biological history. Isotopic signatures in deep-sea sediments reveal spikes in iron-60, a radioactive element produced only in stellar explosions. These signatures coincide with several mass extinction events, including the late Ordovician extinction 445 million years ago, which eliminated 85% of marine species. The supernova responsible for this ancient catastrophe likely occurred approximately 150 light-years from Earth. Computer simulations demonstrate that the explosion would have bathed our planet in gamma radiation for several months, followed by decades of increased cosmic ray bombardment. The ozone depletion would have lasted for centuries, fundamentally altering atmospheric chemistry and triggering a global ice age through reduced greenhouse gas concentrations. Modern stellar surveys have identified potential supernova candidates within our galactic neighborhood. Ik Pegasi, located 150 light-years away, represents the closest known supernova progenitor system. This white dwarf star is actively accreting material from its companion, approaching the Chandrasekhar limit of 1.4 solar masses. When this threshold is exceeded, the star will explode as a Type Ia supernova with devastating consequences for nearby stellar systems. However, astronomical observations reveal a crucial protective factor. The most massive stars, Those destined for supernova explosions concentrate primarily in dense stellar clusters and active star-forming regions. Our solar system's location in the relatively sparse Orion Cygnus arm places us at safe distances from these stellar graveyards. The nearest massive star cluster, the Scorpius-Centaurus Association, lies approximately 400 light-years away, well beyond the lethal radius for most supernova types. Gamma-ray bursts represent the most energetic explosions known to physics, releasing more energy in 10 seconds than our Sun will produce throughout its entire 10 billion-year lifetime. These events occur when rapidly rotating black holes form from collapsing massive stars, creating jets of plasma accelerated to 99.9% the speed of light. The collision of these jets with surrounding stellar material generates gamma radiation, with energies measured in the millions of electron volts. The directional nature of gamma-ray bursts creates a cosmic lottery system for destruction. Unlike supernovae, which radiate energy spherically, gamma-ray bursts concentrate their output into narrow cones spanning just a few degrees. A burst aimed directly at Earth from anywhere within our galaxy would deliver lethal radiation doses thousands of times greater than a nearby supernova explosion. The progenitors of long-duration gamma-ray bursts are hypermassive stars exceeding 25 solar masses, particularly Wolf-Rayet stars that have shed their hydrogen envelopes through powerful stellar winds. These stellar monsters burn through their nuclear fuel in just a few million years, mere moments in cosmic timescales. When they collapse, their rapid rotation prevents symmetric explosions, instead channeling energy into collimated jets that pierce through space at relativistic velocities. Astronomical surveys have catalogued several Wolf-Rayet stars within our galactic vicinity. WR104, located approximately 8,000 light-years away in the constellation Sagittarius, rotates rapidly enough to generate gamma-ray burst conditions. Spectroscopic analysis reveals that its rotation axis may be oriented within 20 degrees of Earth's direction, placing our planet potentially within the destructive cone should this star undergo hypernova collapse. Beyond stellar collapse events, the galaxy harbors another gamma-ray threat in the form of magnetars, neutron stars possessing magnetic fields trillions of times stronger than Earth's. These objects occasionally undergo magnetic reconnection events that release enormous quantities of energy in brief, intense flares. The magnetar SGR 1806-20, despite its distance of 50,000 light-years, produced a gamma-ray flare in 2004 that temporarily ionized Earth's upper atmosphere and disrupted radio communications worldwide. If a similar magnetar existed within 1,000 light-years of our solar system, its flares could trigger atmospheric chemistry changes comparable to moderate supernova explosions. The interstellar medium permeates with high-energy particles accelerated by supernova shock waves, pulsar magnetospheres, and active galactic nuclei. These cosmic rays travel at velocities approaching the speed of light, following complex trajectories determined by the galaxy's magnetic field structure. When they encounter planetary atmospheres, they trigger cascades of secondary particles that can penetrate deep underground. Earth's magnetic field and atmosphere provide substantial protection against cosmic ray bombardment, but the shielding effectiveness varies significantly with solar activity cycles and geomagnetic field strength. During periods of reduced magnetic field intensity, such as geomagnetic reversals, cosmic ray flux increases by factors of 2 to 5. Paleontological evidence suggests correlations between periods of increased cosmic ray exposure and evolutionary bottlenecks in terrestrial species. Young, magnetically active stars produce flares, orders of magnitude more powerful than anything our mature sun generates. These stellar superflares release enough energy to strip atmospheres from nearby planets and sterilize their surfaces through intense ultraviolet and X-ray radiation. Red dwarf stars, which constitute 75% of all stellar objects in the galaxy, remain flare-active throughout their multi-trillion-year lifespans. The proximity of potentially habitable planets to red dwarf stars exacerbates this problem. The habitable zones around these cool stars lie so close that planets become tidally locked, with permanent day and night sides. The combination of tidal locking and frequent stellar flares creates extreme atmospheric dynamics that likely prevent the development of stable climate conditions necessary for complex life. Our solar system's motion through the galaxy periodically carries it through dense molecular clouds and supernova remnants. These encounters alter the local interstellar environment, affecting the solar wind's ability to shield the inner planets from cosmic radiation. Astronomical evidence indicates that Earth has passed through several such regions over the past few million years, coinciding with periods of climate instability and species turnover. The local bubble, a region of hot, low-density plasma surrounding our solar system, formed through a series of supernova explosions approximately 10 million years ago. This structure currently protects us from denser interstellar material, but our continued galactic orbit will eventually carry us beyond its boundaries into regions with higher cosmic ray densities and more active stellar environments. The galaxy contains millions of black holes ranging from primordial objects formed in the early universe to stellar mass remnants created through supernova collapse. These objects move through space following complex orbital trajectories influenced by gravitational interactions with stellar systems and molecular clouds. Computer simulations suggest that rogue black holes pass within 1 parsec of our solar system approximately once every 100 million years. A black hole approaching within the outer solar system would gravitationally disrupt planetary orbits, potentially ejecting planets into interstellar space or sending them spiraling toward the Sun. Even a distant encounter could destabilize the Oort cloud, triggering intense comet bombardments that would persist for millions of years. The geological record preserves evidence of several periods of increased impact activity that may correlate with such gravitational disturbances. Recent observations have revealed the existence of intermediate mass black holes containing hundreds to thousands of solar masses. These objects likely formed through the merger of smaller black holes or the direct collapse of massive gas clouds in the early universe. Their gravitational influence extends much further than stellar mass black holes, creating zones of disruption spanning dozens of light years. The discovery of intermediate mass black holes in globular clusters suggests that similar objects may wander freely through the galactic disk. Their passage through stellar neighborhoods would trigger gravitational chaos, ejecting stars from their original orbits and disrupting planetary systems across vast regions of space. Astrobiological research has identified a narrow annular region within spiral galaxies where conditions favor the development and persistence of complex life. This galactic habitable zone extends from approximately 7 to 9 kiloparsecs from the galactic center, a range that encompasses our solar system's current position. Interior to this zone, stellar densities and supernova rates become prohibitively high for stable planetary environments. Beyond the outer boundary, metallicity drops too low to support terrestrial planet formation. Our location within the Orion Cygnus arm provides additional protection through reduced stellar density compared to the major spiral arms. The Perseus and Sagittarius arms, which bracket our position, contain most of the galaxy's massive star-forming regions and associated hazards. Our inter-arm location grants us a cosmic sanctuary where dangerous events occur less frequently and at greater distances. The solar system's orbital period around the galactic center spans approximately 225 million years, during which we cross spiral arms and encounter varying levels of cosmic hazards. However, our Sun's stable hydrogen-burning phase has persisted for 4.6 billion years, providing the consistent energy output necessary for liquid water to exist on Earth's surface throughout most of geological time. This stellar stability represents a critical requirement for complex life development. Variable stars and close binary systems create fluctuating radiation environments that prevent the establishment of stable atmospheric and oceanic conditions. The Sun's position on the main sequence and its isolation from other stellar objects have created a 4 billion-year window of habitability that allowed life to evolve from simple prokaryotes to conscious observers capable of contemplating these cosmic dangers. Earth's dipolar magnetic field, generated by convection in its molten iron core, deflects most charged particles in the solar wind and moderate-energy cosmic rays. This magnetosphere extends approximately 60,000 kilometers sunward and stretches into a long tail on the night side, creating a protective cavity in the stream of particles flowing from our star. Without this magnetic shielding, Earth's atmosphere would gradually erode through sputtering and ion escape processes, following a trajectory similar to that experienced by Mars after its magnetic field weakened billions of years ago. The combination of magnetic field strength, atmospheric density, and ozone layer composition creates a multi-layered defense system that has preserved surface habitability despite numerous cosmic threats. The catalogue of galactic hazards reveals the extraordinary improbability of stable, long-term habitability for any planetary system. Stellar explosions, gamma-ray bursts, cosmic ray bombardment, gravitational disruptions, and stellar variability create a hostile environment where most worlds remain sterile throughout their existence. The fact that Earth has maintained conditions suitable for complex life for billions of years represents a remarkable convergence of protective factors and fortunate circumstances. Understanding these cosmic dangers provides crucial context for assessing the prevalence of life throughout the galaxy and guides our search for potentially habitable worlds around other stars. The rare combination of galactic location, stellar properties, planetary characteristics, and temporal stability that enabled life's development on Earth may represent one of the universe's most extraordinary achievements. A brief flowering of consciousness in the vast cosmic dark. Four and a half billion years from today, our galaxy will cease to exist as we know it. The Milky Way, that magnificent spiral of 400 billion stars that has remained relatively unchanged for 8 billion years, will undergo a transformation so profound that astronomers have already coined a name for what emerges from this cosmic metamorphosis: Milkomeda. The architect of this galactic apocalypse travels toward us through the void at this very moment. The Andromeda Galaxy, catalogued as Messier 3.1, appears as nothing more than a faint smudge in the constellation of the same name. Yet this deceptively gentle appearance masks a gravitational titan containing over 1 trillion stars, more than twice the stellar population of our own galaxy. Andromeda stretches across 220,000 light-years of space, making it the largest galaxy in our local group and our most formidable cosmic neighbor. Astronomers measure Andromeda's approach using a phenomenon called blue shift. Unlike most distant galaxies, which display red-shifted light due to the universe's expansion, Andromeda's light waves compress as the galaxy races toward us. This blue shift reveals that our neighbour approaches at approximately 110 kilometers per second, or nearly 250,000 miles per hour. While this velocity seems extraordinary by terrestrial standards, on galactic timescales it represents a slow, inexorable gravitational embrace that will unfold over millions of years. The collision appears inevitable because both galaxies reside within what astronomers term the gravitationally bound local group. Unlike the broader universe, where expansion carries most galaxies away from each other, the local group's members remain locked in gravitational partnership. The Milky Way and Andromeda, as the two most massive galaxies in this cosmic family, have always been destined for this encounter. Understanding galactic collisions requires abandoning terrestrial intuitions about crashes and destruction. When galaxies merge, they do not smash together like automobiles in an intersection. The vast distances between individual stars ensure that direct stellar collisions remain extraordinarily rare events. A star measures roughly 1 million kilometers in diameter, while the nearest stellar neighbor to our Sun lies over 4 light-years away. This ratio means that stars within galaxies occupy proportionally less space than marbles scattered across an entire continent. Instead of catastrophic impacts, galactic mergers proceed through gravitational choreography. As the Milky Way and Andromeda approach, their combined gravitational field will begin reshaping both systems long before their stellar disks interpenetrate. Computer simulations reveal that this gravitational interaction will stretch both galaxies, creating vast tidal tails of stars flung into intergalactic space. These stellar streams will arch across millions of light-years, forming temporary bridges between the merging systems. The supermassive black holes at each galaxy's center will play crucial roles in this cosmic drama. Sagittarius A star, our galaxy's 4 million solar mass central black hole, will eventually encounter Andromeda's central black hole, which contains an estimated 100 million solar masses. These gravitational monsters will spiral toward each other in an in-spiral dance that generates ripples in space-time itself. The final merger of these black holes will release energy equivalent to the simultaneous detonation of billions of supernovae, though this energy will propagate as gravitational waves rather than electromagnetic radiation. The merger process will unfold across multiple phases. Initially, the galaxies will approach and begin their first passage, with gravity distorting their spiral structures. Following this initial encounter, they will separate temporarily before gravity draws them together for subsequent passages. Each interaction will further disrupt the orderly rotation that defines spiral galaxies. After approximately 2 billion years of this gravitational ballet, the systems will finally merge into a single unified galaxy. The product of this merger will bear little resemblance to either parent galaxy. Milky will emerge as an elliptical galaxy, lacking the elegant spiral arms that characterize both the Milky Way and Andromeda today. Elliptical galaxies appear as smooth, featureless collections of stars distributed in three-dimensional elliptical patterns. The chaotic gravitational interactions during merger will randomize stellar orbits, erasing the organized rotation that maintains spiral structure. Milky will contain approximately 1.4 trillion stars, combining the stellar populations of both parent galaxies. However, the merger will trigger consequences beyond simple addition. The gravitational disturbances will compress vast molecular clouds throughout both systems, igniting intense bursts of star formation. This starburst phase will consume much of the remaining gas reserves in both galaxies, creating millions of new stars in a cosmic fireworks display that will illuminate the merger for hundreds of millions of years. The new galaxy will span approximately 200,000 light-years in diameter, making it substantially larger than either parent galaxy. Milky will rank among the largest elliptical galaxies in the local group, though it will pale compared to the giant ellipticals found in rich galaxy clusters. The combined mass of dark matter halos from both galaxies will create a gravitational well extending far beyond the visible stellar component. Computer simulations suggest that Milky will maintain active star formation for several billion years following the merger. However, the starburst phase will exhaust most available gas, leaving the galaxy increasingly devoid of raw materials for future stellar generations. Eventually, Milky will settle into the quiescent state typical of elliptical galaxies populated primarily by ancient long-lived stars with minimal ongoing star formation. Our solar system's fate during this galactic cataclysm remains subject to considerable uncertainty. Current computer models suggest several possible outcomes, each dependent on the precise gravitational interactions that will occur during the merger process. The most likely scenario places our solar system in a stable orbit within the outer regions of Milky, potentially 50,000 to 80,000 light-years from the new galaxy's center. However, gravitational perturbations could dramatically alter our cosmic address. Strong interactions with passing stellar systems or tidal forces from the merging galaxies might eject our solar system entirely from the galaxy. Such ejection would transform our solar system into an intergalactic wanderer, drifting through the void between galaxies with no nearby stellar companions. Alternatively, gravitational interactions might drive our solar system toward the inner regions of Milky, placing it in a more crowded stellar environment. The Sun itself faces an additional challenge that operates independently of the galactic merger. Current stellar evolution models predict that our star will exhaust its core hydrogen fuel within approximately 5 billion years. Coinciding roughly with the Milky Way-Andromeda collision timeline. As the Sun transitions into a red giant star, it will expand dramatically, potentially engulfing the inner planets, including Earth. This stellar evolution ensures that Earth's biosphere faces existential challenges regardless of the galaxy's fate. If Earth survives both solar evolution and galactic merger, hypothetical observers on our planet would witness a completely transformed night sky. The familiar constellations, shaped by our current position within the Milky Way's spiral structure, would vanish entirely. Instead, the night sky would display the random stellar arrangements typical of elliptical galaxies. The Milky Way's distinctive band of light, created by our edge-on view of the galactic disk, would disappear as our new location within Milky's three-dimensional structure eliminates this perspective effect. The birth of Milky represents more than a simple collision between two galaxies. It marks a fundamental transition in the cosmic life cycle of our local group. Following the merger, Milky will have consumed or scattered most of the local group's smaller galaxies, establishing itself as the dominant gravitational structure in our cosmic neighborhood. The merger will also accelerate the long-term evolution toward a cold, dark universe. The intense star formation triggered by galactic collision will rapidly consume the remaining gas supplies that fuel stellar birth. Within 10 billion years of the merger, Milky will contain primarily old red dwarf stars and the cooling remnants of more massive stellar generations. The galaxy will gradually fade as these ancient stars exhaust their nuclear fuel and fade to darkness. The supermassive black hole at Milky's center, formed by the merger of both parent galaxies' central black holes, will contain approximately 104 million solar masses. This gravitational monster will continue growing slowly by accreting nearby stars and any remaining gas, but at rates far below the vigorous feeding that characterizes active galactic nuclei in the early universe. Meanwhile, the fundamental expansion of spacetime will continue separating Milky from more distant galaxy clusters. Within 100 billion years, the accelerating expansion driven by dark energy will have carried all external galaxies beyond Milky's cosmic horizon. Future observers within our merged galaxy will inhabit a universe apparently containing only a single galaxy surrounded by empty space, unable to detect evidence of the broader cosmic web that shapes today's universe. The Milky Way-Andromeda merger represents one small chapter in the broader story of cosmic evolution. Similar galactic mergers occur throughout the universe, particularly in the dense environments of galaxy clusters, where gravitational interactions between massive systems remain common. Our local group merger will proceed according to the same physical laws that govern galactic evolution throughout cosmic history. Archaeological evidence within our current galaxy reveals that the Milky Way has experienced numerous smaller mergers throughout its history. The disrupted remnants of ancient dwarf galaxies remain detectable as stellar streams threading through our galaxy's halo. These ghostly trails of stars serve as forensic evidence of past gravitational violence, demonstrating that galactic cannibalism has shaped our cosmic home for billions of years. The approaching merger with Andromeda will conclude the Milky Way's era as an independent spiral galaxy, but it will also initiate Milky's reign as the local group's undisputed gravitational sovereign. This transformation reflects the ongoing hierarchical assembly of cosmic structure, where smaller units combine to form progressively larger systems over cosmic time. In this context, the collision between the Milky Way and Andromeda represents neither destruction nor creation, but rather continuation. The atoms forged in countless stellar furnaces will persist within Milky's stars. The heavy elements essential for planet formation and biological chemistry will remain available for future generations of worlds. The fundamental capacity for complexity and consciousness will survive the transition, awaiting new opportunities to emerge within the merged galaxy's evolving stellar populations. The story of galactic merger thus becomes a story of cosmic resilience and adaptation. While individual structures may transform beyond recognition, the underlying potential for organization, complexity, and wonder persists across cosmic timescales. The Milky Way's legacy will live on within Milky, carrying forward the accumulated history of billions of years of stellar evolution and the precious cargo of heavy elements that makes complex chemistry possible. As we contemplate this distant future, we recognize that the Milky Way-Andromeda collision represents both an ending and a beginning. Our current galaxy will cease to exist, but something magnificent will take its place. The merger will conclude one chapter of cosmic history while opening another, continuing the eternal cycle of transformation that has driven cosmic evolution since the first stars illuminated the primordial universe. The Milky Way galaxy contains approximately 200 billion stars, each one a nuclear furnace burning for millions to billions of years. Yet from the perspective of cosmic architecture, our entire galaxy represents nothing more than a single thread in an incomprehensibly vast tapestry of matter and energy that spans observable distances of 93 billion light-years. Understanding where the Milky Way fits within this larger framework fundamentally alters how we perceive not only our cosmic address, but the very nature of existence itself. Our galaxy does not float alone in the cosmic void. Instead, it forms part of an intricate three-dimensional network known as the cosmic web, a structure so vast that galaxies themselves serve merely as decorative elements along its strands. The Milky Way resides within what astronomers have designated the Laniakea supercluster, a gravitationally bound collection of more than 100,000 galaxies spanning 500 million light-years across space. To comprehend this scale, consider that if our entire galaxy were compressed to the size of a dinner plate, the Laniakea supercluster would stretch across an area equivalent to North America. The supercluster itself consists of multiple galaxy clusters connected by filaments of dark matter and normal matter, with vast cosmic voids separating these structures like enormous empty chambers in a three-dimensional honeycomb. The gravitational influence of this cosmic web determines the motion of our galaxy through space. The Milky Way, along with its local group companions, flows toward a region called the Great Attractor at a velocity of approximately 600 kilometers per second. This motion occurs on top of our orbital dance with Andromeda, creating a complex trajectory through space that would challenge even the most sophisticated navigation systems. Dark matter forms the invisible scaffolding upon which this cosmic architecture rests. Comprising roughly 27% of the universe's total mass-energy content, dark matter particles interact gravitationally but remain undetectable through electromagnetic radiation. Computer simulations reveal how dark matter collapsed first after the Big Bang, forming a cosmic web of filaments and nodes that later guided the formation of the first galaxies 13 billion years ago. Modern astronomical instruments function as time machines, allowing researchers to study the Milky Way's formation and evolution through increasingly sophisticated techniques. The European Space Agency's Gaia mission has revolutionized our understanding by precisely measuring the positions, motions and properties of more than 1 billion stars within our galaxy. These measurements reveal stellar streams and substructures that preserve the fossil record of ancient galactic mergers. Spectroscopic analysis of the oldest stars provides additional archaeological evidence. These ancient stellar relics, formed when the universe was only a few billion years old, contain chemical signatures that reveal the conditions present during the Milky Way's youth. Stars with extremely low metallicity, meaning they contain very few elements heavier than hydrogen and helium, represent survivors from an era when the galaxy had not yet been enriched by multiple generations of stellar nucleosynthesis. The James Webb Space Telescope has pushed observational capabilities even further, detecting galaxies that existed when the universe was less than 400 million years old. These observations reveal that galaxy formation occurred more rapidly than previously expected, with some massive galaxies already established when the cosmos was merely 3% of its current age. This discovery forces astronomers to reconsider models of how structures like the Milky Way assembled from smaller building blocks through hierarchical merging processes. Chemical evolution studies trace how the abundance of heavy elements increased throughout cosmic history. The first stars, known as population 3 stars, contained virtually no elements heavier than lithium. When these massive stars exploded as supernovae, they dispersed carbon, oxygen, silicon and iron into the surrounding medium. Subsequent generations of stars incorporated these elements, gradually increasing the metallicity of the galactic environment and enabling the formation of rocky planets capable of supporting complex chemistry. Visible matter, the stars, gas and dust that we can observe directly, represents only a small fraction of the Milky Way's total mass. The galaxy's rotation curve, which describes how orbital velocities change with distance from the galactic center, reveals the presence of a massive dark matter halo extending far beyond the visible stellar disk. This dark matter halo contains approximately 10 times more mass than all the visible matter in the galaxy combined. Its gravitational influence shapes the orbits of satellite galaxies like the Large and Small Magellanic Clouds, and it played a crucial role in the Milky Way's formation by providing the gravitational wells necessary to accumulate ordinary matter into the structures we observe today. The nature of dark matter remains one of astronomy's greatest mysteries. Leading candidates include weakly interacting massive particles, or WIMPs, which would interact only through gravity and the weak nuclear force. Alternative theories propose axions, sterile neutrinos, or modifications to our understanding of gravity itself. Underground detectors, particle accelerators, and space-based observatories continue searching for direct evidence of dark matter interactions. Recent observations have revealed additional complexity in the galaxy's hidden components. The galactic halo appears to contain multiple substructures, possibly remnants of smaller galaxies that were disrupted and absorbed during the Milky Way's growth. These discoveries suggest that galaxy formation involves continuous accretion of smaller systems rather than a single, monolithic assembly process. Technological advances continue revealing previously unknown aspects of our galactic home. The Rosetta X-ray telescope has detected enormous bubbles of hot gas extending 50,000 light-years above and below the galactic plane, likely generated by past activity from the central supermassive black hole. These structures, known as the Fermi bubbles, suggest that Sagittarius A star was much more active in the recent astronomical past. Radio astronomy has uncovered streams of hydrogen gas connecting the Milky Way to its satellite galaxies, providing evidence for ongoing accretion processes. The Magellanic Stream, a trail of gas stretching across more than 100 degrees of sky, demonstrates how our galaxy strips material from smaller companions through tidal interactions. Gravitational wave detectors have opened an entirely new window for studying galactic phenomena. The LIGO and Virgo interferometers have detected dozens of black hole and neutron star mergers, revealing that these extreme objects are far more common than previously expected. Future space-based gravitational wave observatories will detect mergers throughout the galaxy's history, providing insights into stellar evolution and the formation of compact objects. Advances in computational power enable increasingly detailed simulations of galaxy formation and evolution. Projects like the Illustris and Eagle simulations model the formation of thousands of galaxies, allowing researchers to study statistical properties and compare simulated galaxies with observations. These simulations reveal how feedback processes from supernova and black holes regulate star formation and shape galactic properties. While galaxies number in the hundreds of billions throughout the observable universe, the Milky Way possesses several characteristics that may be relatively uncommon. Its status as a large spiral galaxy places it among the minority of galactic systems, as most galaxies are small, irregular dwarf systems containing only millions rather than hundreds of billions of stars. The galaxy's location within a relatively sparse region of the local group may have contributed to its undisturbed spiral structure. Many similar galaxies show signs of recent major mergers or close encounters that have disrupted their disk structure. The Milky Way's ability to maintain its spiral arms and continue forming stars at a moderate rate suggests a relatively quiet merger history over the past several billion years. The presence of a central bar structure, extending roughly 27,000 light-years from the galactic center, influences the orbital dynamics of stars and gas throughout the inner galaxy. This bar may have formed relatively recently in galactic terms, perhaps within the past few billion years, and it affects the flow of material toward the central regions, where it can fuel star formation or feed the central black hole. The galaxy's metallicity gradient, with higher concentrations of heavy elements toward the center and lower metallicity in the outer regions, reflects the inside-out formation scenario. This pattern suggests that the inner regions formed first and experienced more generations of stellar nucleosynthesis before star formation spread to the outer disk. The collision with Andromeda represents only one chapter in the Milky Way's future evolution. Even after the merger creates the elliptical galaxy astronomers have nicknamed Milkomeda, cosmic evolution will continue reshaping this system over timescales that dwarf human comprehension. Star formation will gradually decline as the supply of cold gas becomes depleted. The merger itself may trigger a final burst of star formation as shock waves compress gas clouds, but this activity will subside as the available fuel becomes exhausted. Within approximately 1 trillion years, star formation will cease entirely, leaving behind a collection of aging stellar remnants. The stellar population will evolve as different types of stars reach the ends of their lives. Low-mass red dwarf stars, which can burn hydrogen for trillions of years, will outlive all other stellar types. White dwarf stars will gradually cool and fade, becoming cold, dark objects invisible against the cosmic background. Neutron stars will slowly spin down, and stellar mass black holes will continue orbiting within the merged galaxy's potential well. Galactic cannibalism will continue as Milkomeda gravitationally captures and disrupts smaller satellite galaxies within the local group. This process will add additional stars and dark matter to the merged system while erasing the individual identities of the smaller galactic components. Positioning the Milky Way within the broader cosmic context reveals both the galaxy's significance and its ultimate transience. Our galaxy represents a successful example of structure formation in a universe dominated by dark energy, the mysterious force responsible for accelerating cosmic expansion. While gravity successfully assembled the Milky Way and its local group neighbors, dark energy prevents the formation of larger gravitationally bound structures. The galaxy serves as a laboratory for understanding fundamental physics. Stellar nucleosynthesis within the Milky Way has produced the full periodic table of elements, creating the chemical complexity necessary for planet formation and biological processes. The galactic magnetic field, generated by dynamo processes in the rotating disk, influences cosmic ray propagation and affects star formation efficiency. Observations of similar galaxies throughout cosmic history reveal how systems like the Milky Way have evolved since the universe's youth. High redshift observations show that massive spiral galaxies were already established when the universe was only a few billion years old, suggesting that galaxy formation occurred rapidly following the end of the cosmic dark ages. The study of our galaxy contributes to broader questions about the nature of dark matter, the formation of supermassive black holes, and the processes that regulate star formation. Each discovery about the Milky Way provides constraints for theoretical models that attempt to explain galaxy formation and evolution throughout the universe. The Milky Way continues revealing new secrets as observational capabilities expand. Upcoming missions will survey the galaxy with unprecedented precision, mapping stellar motions, chemical compositions, and ages across larger volumes of space. The Vera Rubin Observatory will conduct a 10-year survey of the southern sky, detecting faint stellar streams and substructures that preserve evidence of ancient merger events. Future space telescopes operating at infrared and sub-millimeter wavelengths will peer through dust clouds to study star formation in the galaxy's most obscured regions. These observations will reveal how molecular clouds collapse to form stars and planetary systems, providing insights into the processes that created our own solar system 4.5 billion years ago. Advances in theoretical modeling and computational simulations will enable more detailed predictions about galactic evolution. Machine learning techniques applied to large astronomical datasets will identify patterns and correlations that human researchers might overlook, potentially revealing new physical processes or connections between different galactic components. The search for life elsewhere in the galaxy represents one of the most compelling frontiers in astronomical research. As exoplanet detection techniques become more sophisticated, astronomers will characterize the atmospheres of potentially habitable worlds, searching for biosignatures that might indicate biological processes. The Milky Way galaxy, our cosmic home for the past 4.5 billion years, continues its ancient rotation while carrying us through space toward an uncertain but fascinating future. Understanding our place within this vast spiral of stars provides perspective on both our cosmic significance and our responsibility as conscious observers capable of comprehending the universe's magnificent complexity. The galaxy that gave birth to our world and our species will continue evolving long after our sun exhausts its nuclear fuel, ensuring that the story of cosmic evolution extends far beyond any individual world or civilization that might arise within its spiral arms. We began our journey on Earth looking up at a band of light in the night sky. We followed it outward, through star nurseries, past exploding suns, into the heart of a supermassive black hole, and across billions of stars that call the Milky Way home. We discovered that this galaxy is not just a collection of stars. It is a living story, one that began billions of years ago and one that will continue long after we are gone. It gave birth to the sun, to Earth, and to us. Every element in our bodies was forged here, in the fire of stars scattered across its arms. But the Milky Way is not eternal. Someday, far in the future, it will collide with another giant galaxy and become something new. And yet even then, the atoms of our world, the starlight of our sun, and the memory of our species will still belong to this galactic story. As we look back at our home, a small planet in one spiral arm, we are reminded of a simple truth. We are not separate from the galaxy. We are part of it. Its history is our history. Its future is our future. The Milky Way is more than the place we live. It is the cosmic family we belong to, and its endless light continues to call us, to wonder, to explore, and to dream of what still waits beyond.